Hey kids, this video covers the natural logarithm. We call them ln(x) and its derivative. First, let's get started with some basic properties of logarithms. No, not these. These. All right, so properties of logarithms, they're going to be useful in finding a derivative. So we have the ln of a product is equal to the sum of the logarithms of each factor. So the ln of a plus the ln of b is equal to the ln of a times b. If we have the ln of a quotient, it is equal to the ln of the dividend minus the ln of the divisor, provided the divisor is not equal to 0. And if we have the ln of a to some exponent, you can just move that exponent to the front and multiply it by the logarithm. And finally, let's talk about a derivative of a logarithm. So imagine we slap on a nice, juicy derivative operator, and we have the ln of a, we're just gonna, in brackets, put input. You have the logarithm of an input. To take that derivative, this is equal to the derivative of the input all divided by whatever the input is. Now again, this is important, and let's not deviate from that point. Whatever follows the logarithm, that is what goes in the denominator, and the derivative of that input is what goes in the numerator. Now, specific to what we're going to be doing, we can make this look more like something we've seen in class. If we have the derivative of the ln of f of x is just some arbitrary function that is going to equal the derivative of f of x, which we call f prime of x, over the original input, which is just f of x. Notice the ln is not included because it's not a part of the derivative unless the input itself was a logarithm. So this is a pretty easy process to go through. As long as if we first apply one of these three properties, if we can, it makes doing derivatives so simple. I'm going to be working from the textbook again. You can find this on page 331. I am starting with number 49. So number 49 on page 331. So page 331, number 49. We have the function, let's stabilize that, get some focus. We'll go back and forth. Let's say, so we start out with g of x equals the ln of x squared. Now, if we apply our properties of logs, we see we have the ln of some base raised to a power. So the rewrite step could be that this is 2 ln x, which is fine. And then that would mean that the derivative is just 2 multiplied by the derivative of ln x. So it's going to be 2 times. So again, the property for the derivative of ln x is derivative of the input divided by the input. So the input is x, its derivative is 1, and we divide by that original input. That just gives us 2 over x. Alternatively, we could have written g prime like the derivative of x squared, which is 2x, divided by the input, which is x squared. The one x cancels, and we still get 2 over x. So in some cases, writing the problem only makes it longer, and we end up with the same answer. But it's important to see that we could apply either principle and get the same derivative. for number 51, so you know what? Let's call this number 51A. We're going to make this y equals the ln of x to the fourth for 51A. And its derivative is going to be, we're just going to do the derivative of x to the fourth, which is 4x cubed over x to the fourth. And that just reduces to be 4 over x. Over here, if we put a 51b, but this time we make it y equals the natural logarithm of x, and that quantity is raised to the fourth power. Then when we do that derivative, we get y prime equals, and this goes back to using the chain rule. The derivative of anything to the fourth power is 4 times that anything to the third power, and then the chain rule says we have to multiply by the derivative of the inside. And so the derivative of ln x, that's going to be the derivative of the input divided by the input, which gives us 4 ln x cubed over x. Now, we more commonly see the ln of x to the fourth written as ln to the fourth of x, so we don't confuse the 4 with being an exponent for the x when it's supposed to be the exponent for the logarithm. Number 52, we get back into doing stuff like the product rule. So we're going to have, we can make this g of x equals x squared times the natural logarithm of x. And that derivative is product rule. We're going to have x squared times the derivative of ln x, which again is derivative of the input divided by the input. So plus the natural logarithm of x multiplied by the derivative of x squared, which is 2x. It is important to note that the ln of x itself is a number, so it cannot be combined with the 2x to make this the ln of 2x squared. What I'm saying is that this is not the ln of 2x squared. We can't do this conversion. Rather, we can simplify x squared times 1 over x is just x. And to remove that temptation to multiply that, we're going to move that to the front, so we get plus 2x ln x. And even though we're doing this by hand and there is no multiple choice, assume there was, and that the final answer they took out in x, that would be 1 plus 2 ln x, which could further be simplified to x times 1 plus the ln of x squared if we reversed properties of logarithms. I would not do this to you on the test because this is not testing a calculus skill, it is testing an algebraic or pre-cal skill. Number 58 is where we get to start applying some good properties of logarithms. So for number 58, let's go about this 2 different ways. We have f of x equals the ln of 2x over x plus 3. Now, there are 2 ways to work this problem. Let's imagine that we don't remember the properties of logarithms that say that we can make this the ln of 2x minus the ln of x plus 3. And so in doing so, to do this derivative, we're going to write one derivative in, we'll say, light blue, sponsored by Papermate. So we get f prime of x equals, now if we did the derivative of this input, it would be the quotient rule. So we have x plus 3 times the derivative of the numerator, which is 2, minus 2x times the derivative of the denominator, which is 1, over the denominator squared. And that's just the derivative of the input, and we still need to divide by the actual input, which is 2x over x plus 3, which we know that would further simplify to be, we can combine some like terms. We get 2x plus 6 minus 2x over x plus 3 squared, and then we multiply by the reciprocal of this fraction. So that would give us x plus 3 and a 2x in the bottom. And when we further simplify, well, 2x minus 2x is 0, so we get 6 times x plus 3 over 2x times x plus 3 squared, which one of the x plus 3's cancel, so that cancels out, and we get that to the first, and then 6 divided by 2 is 3. So we end up with 3 over x times x plus 3 as our final answer. Now this is dramatically different if we rewrite our function to be, we're gonna go from that blue to this lighter blue, to where we make this the ln of 2x minus the ln of x plus 3. And then if we apply a derivative, we get f prime of x is, so derivative over original minus, again, derivative over original. And this just equals 1 over x minus 1 over x plus 3. And so we could get a common denominator, and even though you could stop right here, we'd have to multiply this by x plus 3, so we get x plus 3 minus x over x times x plus 3, and we get the same answer, 3 over x plus 3. Ooh, wrote all of that out of the frame. Excuse me, kids. So if we rewrote this as ln of 2x minus the ln of x plus 3, the derivative would be the derivative of 2x, which is 2 divided by 2x, minus the derivative of minus the derivative of x plus 3, which is 1, divided by x plus 3, which the 2 over 2x cancels to be 1 over x. And here, if we get a common denominator of x times x plus 3, you effectively multiply this by x plus 3, you multiply that by x, so we get x plus 3 minus x over that product, and that simplifies to be 3 over x times x plus 3. Oh, still out of frame. Zoom out just a bit. Okay. So the next example is, what if you had a logarithm inside of a logarithm? Oh, want to know more, kids? Imagine we come along for number 61, and we're told that y equals the natural logarithm of the natural logarithm of x squared. So these nested or layered logarithm problems tend to give students trouble, but we're just going to keep applying the consistent concept of the derivative of a logarithm that has an input is the derivative of the input divided by the input. So in this case, our input is, we can make a note if we want, you can spell input. Input equals the ln of x squared. And so the derivative of the input is, well, it's the ln of x squared, so that's going to be 2x over x squared, which is 2 over x. So that's what we're going to do over here. So the derivative of a logarithm is the derivative of the input, which is 2x over x squared, divided by the input, which is the ln of x squared. First, that's going to simplify to be just 2 over x over the ln of x squared. But you know Mr. Martin's rule, if you have a divided by b divided by c, we can make that a over b times c. And that's our final answer. Because it never goes anywhere, let's do number 84. And this will be the last problem we work in here. we're going to connect the concept of implicit differentiation with the concept of the derivative of a logarithm. So for number 84, we have the function is the ln of x, the product xy plus 5x equals 30. And assume that when let's find the derivative at a particular point. So when when y equals 1, we could easily find that x equals 6. Nope, that's not true. Could we make, if x is 1 and y is 1, if x is 1, that's going to be if y is 1, you get the ln of x. We don't have an easy point for this, so don't worry about that. Let's just do the derivative, I suppose. If we apply a derivative operator, we're going to get 4. So couldn't we first rewrite this to be the ln of x plus the ln of y to avoid doing the product rule? The answer to that question is yes. So that's what we'll do. So we're taking the derivative of ln x, which is derivative over input, plus the derivative of y, which is dy over dx over the input plus 5 equals 0. So if we move out all of this other stuff, let's say we have, so we're gonna have dy over dx times 1 over y, and that equals 5 minus 1 over x. So I'm not a big fan of having things that aren't fractions with things that are fractions. So let's take a moment to rewrite. So we get dy over dx equals 5x minus 1 all over x. You know what? Include the 1 over y, right? So we're solving for dy over dx. We need to divide by 1 over y, which is the same as multiplying by y. So we get dy over dx is 5x minus 1 over x multiplied by this reciprocal. So that's going to be y over 1, which would just give us y times 5x minus 1. And that quantity is divided by x. Do we have a last example where we can use implicit differentiation to find the equation of the tangent line? Sure. It is problem number 87. So in this, the final problem that I said was the final problem in the previous step, we have x plus y plus, well, minus 1, excuse me, minus 1 equals the ln of x squared plus y squared minus 10. So the ln, so x plus y minus 1 equals the ln. I'm looking at the wrong example. Oh, we don't need the 10. Excuse me. I looked at 2 different examples. So, and we're doing this at the point 1, 0. 1, 0. We're finding the equation of the tangent line at 1, 0. So you cannot distribute and tell me this is the ln of x squared plus the ln of y squared. That is not how this works. You have to leave this alone. There's no multiplication, so you can't expand it. So if we drop a derivative operator around the entire equation, we get, also used to the 1 over x, I almost wrote that. We get 1 plus dy over dx, the derivative of negative 1 and 0, equals derivative over original. So derivative of the input is 2x plus 2y dy over dx over x squared plus y squared. And we want to write the equation of the tangent line, which requires that we have the point, which we're given, and the slope, which means that we need dy over dx at that point. So it's easier to substitute in 1 and 0 instead of trying to solve for dy over dx. So we would get 1 plus dy over dx equals, if x is 1 and y is 0, this entire term is going to turn to 0. So we get 2 over 1 squared plus 0 squared, which is 1. And that would imply that 1 plus dy over dx equals 2. So dy over dx at the particular point is equal to 1, because we just subtract 1 from both sides. So to write our equation, we have y minus 0 equals the slope, which is 1 times x minus 1. That's the equation in point slope form. So a quick recap of the logarithm. First, we have the properties of logs, where we have the ln of a product is the ln of the sum of the logarithms of the factors. The ln of a quotient is the ln of the numerator minus the ln of the denominator if the denominator is not equal to 0. And the ln of a power is the exponent times the ln of the base. The derivative of a logarithm that has an input is the derivative of the input over the input. Now, if this was a constant, it would just be 0. Otherwise, it's going to be derivative of the input over the input. So that concludes this video. Thanks for watching.